All right. I'd like to welcome you to this video where we are dealing with rational functions, but specifically dealing with oblique or slant asymptotes. So let us dive right into it. So in the previous examples, we've done horizontal asymptotes and vertical asymptotes. In this section, we'll be dealing with oblique asymptotes. So essentially, let's have a look here on the side what an oblique asymptote essentially looks like. So this is just an example of it. An oblique or slant is an asymptote which is given by a straight line. So let us say we had a function which is going that way and another one which is going that way, but there seems to be an asymptote in this direction, boom, 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 which is given by the equation of a straight line. So that is what we call an oblique asymptote. So I'll use it as OA. Oblique asymptotes are OA in this case. So let us dive into this. Let's see how we are able to find these oblique asymptotes. So let us start off. Firstly, I've got a function or a rational function which is given by P over QX. So the most important thing I want you to know first, if the degree of P of the numerator is the same as the degree of the denominator, what we normally say is that there exists a horizontal asymptote, and normally that horizontal asymptote is given by the equation y equals to L. I'm just simplifying this, not getting into deeper definitions. The degree of P, if the degree of P is like 1 less or slightly less than that, than the degree, so we can say 1 less, then the degree of the denominator, we say there exists a horizontal asymptote, but this horizontal asymptote is given by the line y equals to 0. Okay, and that'll be just a normal way of us calculating that asymptote. But now we're going to deal with this when the degree of the numerator, P, is 1 more than the degree of the denominator. And this is quite important. It is 1 more than the degree of the denominator. If this is the case, there exists an oblique asymptote, and the oblique asymptote will be a straight line. And we can get deep into what that means and how we're able to find that. So think about it. So what we will then do, we will use the method of long division, and we'll try and divide this rational function. So when we use the method of long division, what happens is that we divide P, which is the numerator, and then we end up having a term kx plus the remainder of that over q of x. So essentially what you can conclude is that this quotient that you get is the oblique asymptote. And that is what you can come up with. So all you have to do in rational functions, you find that the degree of the numerator is 1 more than the degree of the denominator. You can be assured that there will exist an oblique asymptote. And then how do you find out what that asymptote is? You apply long division, and then you get it into effect where you can calculate the quotient and the remainder. That quotient is the one that's going to give you the oblique asymptote. There is a much more deeper definition of this, but for our course, this is essential that you know that. So let us dive deep into doing these two questions, and we can see the oblique asymptotes. I've also drawn these two functions on GeoGebra, and we'll see what those look like. So let us dive right into it. So what we'll do, like we said, we'll perform long division on this expression. So x squared plus 3x plus 2. We've got x minus 2. Our long division, x goes into there once, comes back there. We get x squared, we get minus 2x. And then we have to subtract the whole thing. But when we subtract the whole thing there, we get a 5x. We bring the 2 down. And then our next line, we check what that is. We get a 5 there. And then if we multiply back, we get 5x. And then multiply with the 2, we end up with minus 10x, minus 10. And if we take a subtraction of that, we end up with 12. So what that means is that the function that we have there, x squared 3x plus 2 over x minus 2, can be written as x plus 5, in this case, plus 12 over the same numerator, x plus 5. So now what we are trying to emphasize is that this part over here, the quotient of this, is our oblique asymptote. So we can say that the oblique asymptote is given by the equation y equals to x plus 5. And now we'll show you this in a diagram once we deal with the second question. So let's dive into the second question. In the second question again, we see if we want to determine the oblique asymptotes. I keep forgetting that. So the oblique asymptote is what we're looking for. And therefore, we will use long division again. Minus 4x squared minus 2x plus 1. This will be x squared minus 1. So x3 goes into the x times. This gives you x to the 3. And then x that. So this gives us minus x. So if we subtract everything there, we end up with just minus 4x on this side. Minus minus gives us minus x, and then we want to bring the 1 down. So this is the 4x squared again. And then what we want to do next on this is to see how we can, 4x squared goes into the minus 4 times. This is minus 4x squared. If we multiply that, that gives us plus 5. And if we go down, we get minus x. And if we try and subtract that, we end up with, this is 4. If we subtract that, we end up with minus 3. So what this means is that the expression that we have there, x to the 3x squared minus 2x plus 1 over x squared minus 1 can be split up into x minus 4. We'll take the negative out, so this becomes x plus 3 over x squared minus 1. Again, I want to emphasize that this is the oblique asymptote. And one thing that I needed us to realize is that the degree here was 3 to the 1 on top. So we know that an oblique asymptote will exist. The degree is 2, there's 1. The oblique asymptote will exist. And therefore, we say that the oblique asymptote here is given by the equation y equals to x minus 4. I hope this has created some understanding of how we find the oblique asymptotes. Now let's get into GeoGebra. I've sketched the two functions there, and this is what the two functions look like. So the first function looks like that. So this is given by that oblique asymptote y equals to x plus 5. And this is given by that oblique asymptote y equals to x minus 4. And this is what the oblique asymptote looks like. So what you'll be able to do is to sketch functions now where it involves an oblique asymptote. So in the next video, we'll pick up a question and we'll use derivatives and we'll use asymptotes, and then we'll be able to get that entire function to see what it looks like. I hope this has made sense on how we find the oblique asymptote and what it is, and therefore I shall see you in the next video.